for the very inspired things for working on Alibaba Cloud with Apache Flink. So, and let's continue with the next topic. And the next topic is one of the I'm most looking forward to. And so let's welcome Venkana, a senior software technology expert at LinkedIn, and he will share the charting new territory, LinkedIn's early bet on Flink batch for large-scale workload. Okay, welcome, Venkana.
Thank you, Jack. Good afternoon, everyone. I'm Venkat Saurirajan, working at LinkedIn, and I'm going to talk about LinkedIn's early bet on Flink batch and how we scaled it for large-scale workloads. Before we dive into the talk itself, let me give a bit of a background about me. I have been building and scaling distributed data systems for over a decade now, and I'm currently building stream batch unification at LinkedIn. And before this, I have worked extensively on Spark, especially contributed to Spark's push-based shuffle. In the next slide, let's look at today's agenda. So first up, I'll set up the stage with respect to the problem context, what were the challenges we faced with and why it required a new solution. And then I'll talk a bit more, basically motivate about why we wanted to build a unified stream batch platform and why Flink is a natural fit for that. And I'll do a brief overview of Flink batch architecture and then a deep dive on one of the real world ads use case at LinkedIn and how we scaled it with Flink batch. And finally, I conclude the talk with the results we saw and summarize it with takeaways that you can leave with and also use it at your company. Let's dive into the talk itself. The problem context, right? So at LinkedIn, we have been seeing exponential usage of Flink streaming, and naturally for all these Flink streaming use cases, it also requires periodic batch processing, either for bootstrapping a new model or fixing the bugs or handling late events, things like that. So far, at LinkedIn, for all batch processing, Spark has been the de facto, and Flink for streaming. So, any sort of batch processing has to be done through Spark, and streaming has been done through Flink. This meant there is a split ecosystem. So the user's business logic has to be written in two different DSLs. It required a dual infra, the debugging complexity. There is no unified way to test the code changes, and also introduces inconsistent data semantics. Yeah, now that we set up the stage with the problem context, let's see what our end state, our grand vision is. Ultimately, we want to build a unified stream and batch platform, and we realized we need to have this unified stream and batch platform in order to simplify the challenges our users are facing as well as our platform teams are facing by managing multiple different infras, and also supporting all the issues with respect to inconsistent data semantics and things like that. So initially we tried building API unification. So basically simplifying at the API layer, so that users just need to author their business logic through an API, and eventually that gets translated underneath either to Spark or Flink accordingly based on the use case requirement. But we quickly realized this is not scaling or working at large scale because of the inconsistent data semantics that I alluded to in the previous slides, as well as like a lot of debugging complexity. Users have to know two different engines, and like there were lots of those challenges. So we quickly realized like we had to like come up with like a one engine strategy to solve for a unified stream and batch platform. This simplifies this simplifies the deployment, and it also unifies the testing. Users just need to know need to know one single engine, like in terms of debugging or authoring their business logic, and like also they can leverage the same set of tooling across for both their batch processing and stream processing use cases. Now that like we discussed about our vision of unified stream and batch platform, let's see why Flink Batch. Even though open source was also moving the direction of unifying stream and batch with Apache Flink, we quickly realized like Flink Batch to be like a natural fit for our use case as well. Not just because of OS's strategy around stream batch unification, we also did multiple POCs to basically run against Flink batch for large scale data, and it did show promise. It has this modern SQL optimizer built on top of Apache Calcite, and also it worked well at large scale. Like having said all of that, I still have to mention like there were like bunch of issues we figured out like as part of our POCs, but we decided we'll fix them along the journey. Now that we saw like why Flink Batch, let's quickly do a quick overview of the key components in our Flink Batch platform. At the core is the Flink engine for both batch and stream processing, especially batch, given the focus is on the batch in this talk today. And then we leverage Iceberg for our data lake for all the tables, and it is highly customized, and therefore we have built a custom Iceberg connector. And then we have Scalable for our shuffle service. I'll do a deep dive on Scalable more in the later slides. And for workflow orchestration and scheduling the jobs, we leverage Airflow. This has been used in the past as well for all our batch processing workloads, specifically Spark. And finally, for observability, we are leveraging Flink Issue Server. It didn't scale, so therefore we had to enhance it to support at large scale, to support like large number of workloads at LinkedIn. Let's do a quick overview of Flink Batch architecture at LinkedIn. So at LinkedIn, we are strategizing on SQL first across our data platform, and therefore even for our unified stream and batch platform, we decided to go with Flink SQL. So Flink SQL is the recommended API for the end users with the support for custom UDFs. For the batch, for workflow orchestration and scheduling the jobs, like I mentioned, we are leveraging Airflow. We have a custom control plane that basically receives the job submissions, validates them, authenticates it, does authentication, authorization, and finally submits the job to the cluster manager itself. At LinkedIn, we are heavy users of Yarn until now, so we are running Flink Batch on Yarn as well, but we are also in the process of migrating to K8s. So once the batch control plane submits the job to the Yarn resource manager, it brings up the Flink AM with job manager in it, brings up task managers negotiating with the Yarn resource manager to compute the business logic. And like I mentioned, we use Iceberg for our data lake. So it reads and writes from the Iceberg tables in HDFS and does shuffling through Scalable for intermediate data. And finally, once the job completes, it writes something called job archives, which are nothing but a JSON file containing all the necessary job metadata, metrics, logs links for troubleshooting, so that like users can review the completed Flink application for any portion analysis. So now that we did a recap of Flink batch architecture at LinkedIn, let's dive into the let's do a deep dive on one of our real world use case. So in this use case, this use case is basically like to train model for our LinkedIn ads, and this particular job is primarily dealing with like model training data generation. Let me give a quick overview of the high-level business logic that this job actually operates. It fundamentally does a three-way join against like 4 different event streams: scores, like ad scores, ad impressions, clicks, and video events. So we run this job both as a stream processing job as well as a batch processing job. This stream processing job like continuously receives the incoming events, processes them, and like generates these ad training data events. But periodically, time to time, like to fix bugs or handle late events, or or when the streaming pipeline is down, we need to backfill, and like which is where the batch processing job comes into the picture. Given the focus is on the Flink batch, I'll do the deep dive more on the Flink batch aspects. So the batch processing job like seamlessly consumes the data from the underlying iceberg tables. So each event stream is continuously ingested into data lake as iceberg tables, and joins against these 4 tables to produce the ad training data. Quickly point out the key characteristics of this job, as well as the data, and will connect like how these characteristics actually brought out interesting challenges, and like how we tackle them in the later slides. So the input tables actually scale unevenly. So some of the tables were smaller, like in the order of GBs, while the other tables were massive. And these tables had like deeply nested file structure. Partly this is because of our schema and the scheme of the Kafka topic itself. And finally, the business logic requires like understanding the nested collections, which led to data explosion in the intermediate vertices. Let's see the interesting challenges like one by one, and talk more about like how we solve them. So first up is the connector scalability, mainly on the read side of things. Like I mentioned, like we have this complex nested schemas, and like also the large volume of data. So this brought about 2 interesting challenges, mainly on the I/O throughput, and also like significant overhead on the deserialization path. I'll do deep dive on this in the next set of slides. The first thing is the need for nested filter pushdown. Flink didn't like out of the box support nested fields filter pushdown. It also supported it also had support for filter pushdown. So this was very critical, given this business logic had like filters on the nested fields. Without that, when we ran it like out of the box, the job had to read all the input data and then like later had to filter, which significantly degraded the overall throughput. So the solution is basically to implement add support for nested fields projection pushdown, both at Flink as well as on the connector layer, which we eventually contributed back to open source as well. So once we had this optimization, this dramatically boosted the I/O throughput, because this filtered out like almost 90 to 95% of the disk seeks, as it is only reading reading and deserializing the data where the filter matches. So now, so with the nested filters pushed down, like we were able to tackle the challenge of filtering out like unused rows, but like we still had this problem of reading unused columns. So which is where the nested projection pushdown comes into the picture. So in this case, like all the Flink had support for nested projection pushdown, but the Iceberg connector itself didn't have it. So therefore, we had to we had to add like support for nested projection pushdown at the connector layer to avoid this unnecessary deserialization and then like projecting out like the unused columns at a later point. We are planning to contribute this back to Iceberg in the future, but this gave like additional boost to the overall throughput, like along with the nested filters pushdown. So far we saw like the optimizations done at the SQL, like Flink SQL layer and the connector layer, but we still saw IO throughput bottlenecks, mainly on the connector layer. In this case, it's mainly due to the like Iceberg connector design. The IO connector, like the connector design itself has like an interesting aspect, which is basically it had two different threads. One for input splits, fetching and deserialization of the splits into corresponding rows, and finally the task thread, which operates, which basically applies the business logic on top of it. Due to the underlying file formats, a requirement to reuse the objects to overall improve the throughput, it required like costly copies in order to avoid any race conditions. But this significantly affected the overall throughput. Therefore, we re-implemented the connector, wherein like instead of deserializing on the fetcher thread, like we delegated it to the task thread to do the deserialization, and this actually improved the throughput like as much as up to 2x in this case. So far we have seen like all the scalability improvements, like on the challenges, the challenges and the scalability improvements we did on the connector layer. Let's look at the challenges we faced on the shuffle layer. And like in terms of the key characteristics of this job shuffle, we initially started with Flink native shuffle, which is basically the job itself shuffling the data necessary for the batch job. And like there is a large volume of shuffle data that gets generated. I would be interchangeably using shuffle and intermediate data, but they're nothing but the same. And this shuffle is actually hosted alongside with HDFS. So two challenges it brought out, which is basically like any task manager failure due to node loss, either due to planned maintenance or unplanned maintenance, required recomputation of the previous stages, and also and also noisy neighbor effect due to IO contention, given they are co-located. Let's look at these challenges more in detail in the next set of slides. So first up, like I mentioned, like we have this co-located shuffle and like how it significantly degraded the overall fault tolerance. Any worker loss, any compute node loss meant that like it has to recompute the previous stages. And given in our fleet, like with large scale deployments, we had like huge number of nodes, and like there will be a constant node churn leading to node failures, and therefore like this job continuously recomputed the previous upstream vertices data, leading to increased overall runtime, and like sometimes like the job itself would fail because of lots of retries. And another issue is basically the noisy neighbor effect. So we quickly realized like we need like an external shuffle service, and at the same time we were also exploring disaggregated shuffle for our Spark needs. So this is when we decided to build like a common shuffle service for both Spark and Flink. After doing like multiple POCs using different shuffle services, we narrowed down on Scalable. Like this out of the box had like support for both Flink and Spark, even though we still had to extend like add support for Flink 1.16 at that time. It greatly improved the overall fault tolerance, and in cases it actually in this case it also gave a throughput improvement of up to 2x. It was not all rosy. Like there were still challenges we had even with Scalable in terms of fault tolerance. Let's look at that in the next slide. So with Scalable, any worker failures weren't propagated quickly back to the engine for immediate recomputation of the intermediate data. Due to that, it continuously retry the same task on a different node, wasting the retrace and without making any progress. So we improved this. We actually enhanced this fault tolerance by surfacing up the worker failures back to Flink so that it can immediately schedule recomputation of the missing data and then thereby making progress. So this on top of Scalable enhanced the fault tolerance for this job further. So along this journey, we also experienced a subtle data correctness issue. So this actually manifests in an interesting way, which is basically when the join has binary key as one of the join fields, and the job manager and the task manager has different JVM heap sizes, mainly one greater than 32 gigs and another lesser than 32 gigs. Why is that? This doesn't make sense, right? The key issue here is Flink leverages, especially for batch processing use cases, things like code generation and JVM internal APIs unsafe library. So the job manager actually does the code generation and ships it off to the task manager to get executed. Whenever the memory, whenever the heap sizes are different, the offset alignment were also different, since it is directly accessing the memory locations instead of going through standard Java APIs. So due to this, the offset information that gets sent to the task managers were not aligned with how they read the data, leading to shuffle of this data to incorrect partitions and thereby producing totally wrong output. So we fixed this subtle but nasty shuffle correctness issue and also contributed that back to open source. This was more of a ticking time bomb that we had to narrow down the root cause and fix. And with this, we were able to tackle the data correctness issue on the shuffle side, as well as enhance the fault tolerance and improve the overall throughput of the Flink job itself. Now that we saw the connector and shuffle side scalability improvements, let's quickly see the scheduler side, mainly on the tuning of parallelism. So like I mentioned earlier, we are dealing with large volume of data, but there is one interesting bit, which is basically after the first join step, there is a significant reduction in the data size. And also there is a high variability in the intermediate data value. These two characteristics of the job actually brought about two interesting challenges. Mainly tuning the parallelism for different intermediate data sizes becomes difficult, and also another thing is the source vertex and intermediate vertices require independent scaling, because we can have huge amounts of data to be scanned, but the data that gets generated at a later point in the job can go down. So let's look at this in the detail. So we began with default scheduler with fixed parallelism, but with uneven state sizes, like it only added like more scheduling overhead, and like also like had like throughput issues. So which is when we decided to try out adaptive batch. Like in our POCs with adaptive batch, the job like could automatically tune the parallelism for the intermediate vertices. This reduced the overall scheduling overhead, and also kept and also reduced the overall bookkeeping pressure on the job manager side itself, which meant like the resource profile of the job manager can be a lot smaller than with default scheduler. So even though the adaptive batch worked, like it worked fine eventually, it did require tuning the adaptive batch configs, especially the average data volume per task, without which it was running out of memory. I'll quickly run through the slides for due to the time reasons. Next up, like this is another interesting issue, which is basically the adaptive batch had this cap on the source parallelism by the intermediate max parallelism. So like source and like intermediate vertices are like totally independent. Like source vertices consume data from the external storage, while the intermediate vertices consume data from the shuffle. Therefore, they can have different scaling and different parallelism. So we had to basically fix this issue so that like we could independently scale the source and downstream vertices independently. Like in our case, like where we are dealing with large amounts of input data with different parallelism, like the source vertices can be, like the source vertex can consume the input data lot faster compared to the intermediate vertices. Like having like higher parallelism on these intermediate vertices, like where the amount of data that gets generated is less, is only going to add overhead. So therefore, like having this independent scaling made a lot of sense in this case. Yeah, now that we saw like the different challenges we faced on the connector, shuffle, and the scheduler side, let's quickly see the observability aspects. For any service or any system, like observability is very key, and that is true to Flink batch applications as well. We leverage Flink History Server for we leverage Flink History Server for the observability. And we had one key requirement, which is basically to support a large number of Flink applications, and also Flink applications that have high degree of parallelisms. So one immediate challenge, or a scalability challenge that we were hit with is the scalability limit. The Flink History Server scaled well for small jobs, but the moment like the jobs had like high degree of parallelism, it had scaling limits. Let's see that more in detail in the next slide. So Flink History Server leverages the local file system to expand the metrics into directories and file structure. It sort of used it as a key value system. Like especially in the case of Flink jobs that have high degree of parallelism, it quickly runs out of inode limit. So therefore, we built a custom storage backend using RocksDB instead of writing it down as a file, like as the metrics for individual tasks. This becomes like a key value pair within the RocksDB itself. This nicely scaled well for this particular job that has high degree of parallelism, and also it scaled really well for large number of applications that we run on our platform. So although with RocksDB, we could scale Flink History Server well, it still had, the local cache still had like a storage limit. Like, so it can cache so much only, beyond which, the older applications won't be available in the Flink history server. Especially in a large-scale deployment, it quickly goes out of cache due to the local cache limit. So we recommend a hybrid implementation of this job archive fetch. Basically, if it is available in the local cache, render it. If not, fetch it from the remote storage and locally cache it. This uses a LRU style cache invalidation. This both improved the overall observability user experience and also kept the local cache bounded. So finally, even though with RocksDB and also having this hybrid job archival fetch, it improved the overall scalability and the user experience in terms of observability. We still had an issue in the Flink history server, which is basically coupling the local cache expiry with the remote storage solution. So this meant the remotely stored job archives are prematurely deleted and leading to unavailability of history of slightly older applications. So this required a fix to decouple the local cache, local cache expiration from the remote archive retention. Once that is fixed, this enabled longer job history retention on the remote storage, and also kept the local cache bounded with a local cache limit. Yeah, now that we saw the challenges and the improvements along different dimensions with respect to the Flink batch, let's see the results we saw for this particular job. So initially, when we started, we were when we tried to run with vanilla Flink. So we ran this job to generate 1 day worth of data, one day worth of ad training data even, which is roughly about 30 TB on disk compressed. But when it is read in memory, it explodes 50x. So sort of going into the petabyte territory. This job failed more than 50% of the time. And even the times when it ran fine, the runtimes were erratic. So once we had these improvements made on the connector, shuffle, and the schedulers side, we were easily able to run 7 days worth of training data generation, translating roughly around 200 TB of on-disk data compressed. Consistently and successfully. I mean, successfully, consistently, with sub 10-hour runtime. So not just that, we are also very confident that this job can scale even further, with organic data volume increase. So finally, to conclude with key takeaways. Our early bet on Flink to unify stream and batch definitely paid off. It simplified the overall development and operations. It also made it easy for our end users to only author in one system, deal with one system, and the learning curve is also brought down substantially. With Flink batch, with all the optimizations that we discussed, we could prove ourselves that it can deliver massive performance gains. There is also still a lot more work that can be done to improve it even further. But one thing to point out, all this is not it's not out of the box. It still requires a deep internal expertise, especially the correctness issue that I discussed earlier. So it to operate Flink batch at scale, it still definitely requires deep subject matter expertise. And finally, the scalable observability is very critical for any platform, and that is true for Flink Batch platform too. And last but not least, like whatever the fixes or improvements that we make internally, we also want to contribute that back to the community, not just for the community. Not only to improve the overall community, but also to streamline our internal platform itself. That's it from me. Thanks for being a great audience. Are you still being skeptical about Flink Batch? I'm happy to answer any questions. Thank you.
Thank you, Venkata, for walking us through the amazing journey, forward-thinking adoption of the Flink Batch. And because of time, we don't provide the QA. Yes, but let's take a 10 minutes coffee break so you can connect with the speaker for further communication. And we'll come back here at 15:45 for the second half of the session. Thank you. I see you soon.